Right. So, having a nice weekend. So, so today we're going to continue talking about graphs and try to solve some new problems concerning, well, not street problems, but we're going to do other types of graph theory types of problems. First, we're going to finish this section, chapter 5, and we have a couple of things to get through to do that. So last time we had Euler's theorems. Let's recall where we ended. Two theorems. And these were theorems that told us whether or not we had an Euler path or an Euler circuit for a given graph. And it was not a hard thing. You just had to look and see whether basically all of the vertices were even. That meant that we had an Euler circuit, assuming we had a connected graph, or at exactly 2 or off, and we had an Euler path. Again, for a connected graph. So while that was very nice, it gave us a sense as to whether or not there was a solution to the problem. We didn't necessarily know how to solve the problem. Knowing there exists a solution is not the same thing as knowing how to do it. So today we want to talk a little bit about how to do it. And this is this Fleury's algorithm. So this is a step-by-step process to be able to do this. So the steps are first, or maybe 0th step, is check Euler's theorem. Make sure you have a solution before you try to solve it. 0th step. Now, if we've completed that successfully, we do have a solution, and our first step should be choose a starting vertex. And this will depend on whether or not we're doing this for a path or a circuit. Right? The path, and then we want to choose one of the odd vertices. Circuit, we can choose any. Okay. Now, second, and the step that gets repeated over and over again until you're basically done, is to choose what edge you're going to travel along. And here, there's only one rule. So choose any edge except a bridge to the untraveled part. I'll explain. And that this, of course, is unless you have. I don't know why I'm saying that. I'll just if you have to, you have. The next step is just repeat. So you're going to repeat to second step until you're finished. And then the nth step. Nth step is whatever n is. So I'm going to illustrate this with an example, and hopefully it'll help. All right, so we're going to draw a graph with 7 vertices. Like these nuclear power plant signs or something. I don't know. Okay. So let's say I wanted an Euler circuit here. Okay. I want to see if there's an Euler circuit. This is my graph. So who can tell me whether the 0th step, I'm successful at completing the 0th step? Yeah, Euler circuit. Yeah. Right, very good. All of them are even. So this one, all of these guys have degree 2, meaning there are 2 edges coming into each of them, right? That's how we count the degree. This one here in the middle has 1, 2, 3, 4, 5, 6. So that's also even. So all of the vertices are even. So indeed, 0th step, we're successful. Okay, now we need to just choose a vertex to start at. Okay, so tell me, does it matter where I choose the vertex? Start at. Okay, not necessarily, yeah. Okay, that certainly gives you the most choice. So this depends. And the answer is, I mean, it would depend on the problem. If you had extra parts of the problem, maybe you do want to choose a particular kind of vertex. But if you're just after an Euler circuit, it shouldn't matter where you start, assuming that Euler's theorem holds. So on the other hand, if we're doing the path version, not the circuit version, in other words, we're starting at a different point than we're ending, then it does matter. Then we need to start at one of the odd vertices, one of the 2 odd vertices. So I'm not doing that this time, but so here it doesn't matter. So I will just choose, say, this guy here. That's my starting vertex. This is my first step. I'm going to take my second step and I'll make a green path. My second step, I have to choose a path, an edge to traverse, but it can't be a bridge to an untraveled part. Well, I haven't traveled anywhere yet, so everything's the untraveled part, and there's no bridges connected to this edge or to this vertex. So I'll just travel here. Now, what I'm going to do, so this is my second step. I chose an edge. Okay, so now what I'm going to do is I'm going to take this. I'm going to modify the untraveled part. I traveled along that green edge, so that is a traveled part. I'm going to get rid of it. Okay, but now I'm at this point here. I just traveled over there. Now I need to choose now I need to repeat the second step. Choose a bridge. Everything here is the untraveled part. So or choose something that's, pardon me, sorry guys. Choose an edge that's not a bridge, not a bridge. So let me ask you guys, can I choose any edge here? I cannot choose any edge. What edge can I not choose? Yeah, the one going down. I can't choose this edge. That's a bridge, right? If I got rid of that, I'd have this guy and this graph. I'd disconnect that graph. That's what a bridge does. It's something that if you delete, you disconnect the graph. So I cannot choose this guy. I have to choose, but I choose anything else in this case. So I'll choose this guy. I'm repeating my second step. I go ahead. I encourage you to burn your bridges. Sorry, that's sorry. Here I don't have a choice, right? Here I have to travel along one edge, that's it. Burn that guy. If I'm going to take that edge out, I'll also take any points that don't have any edges left. So I will get rid of everything. Here I don't have a choice again. A little faster. Okay. As I travel, I have to get rid of things. So here I do have a choice now, right? So here I'm in this setup here. I have to choose again something that's not a bridge. This guy is still a bridge, right? That's still a bridge. So we can't, we don't want to choose that, but these two, we could choose either one of them. So let's choose, say, this one. Okay, traveled over here. Get rid of that. We're now at this point here. Sorry, we gotta get rid of that guy too. You don't have any choice. So if you go here and say, then we won't have a choice and we'll have to go there. Let me just do 2 steps at once. I'll be all the way back here. Again, I don't have any choice for the next 2 steps. I'll go here and here. So if I go back now and I follow my algorithm, I can go ahead and order the edges. So I started going here, 1, and I went here, 2. I'm just following this step. I'm looking at what I did. 3 here, 4 here. I decided to go here for 5, 6, 7, 8. That gives me an ordering of the edges that I do. Is it clear? Questions? Yes. No. I'm just doing it perhaps to be confusing, but I'm just trying to take it 1 step at a time, or at the end 2 steps at a time, just to show you that it's. I think in math, all the thing to do is to do things really slowly and painfully at first, and then as you get better at things, it gets faster and you don't have to do. You don't have to go over all the details later, but at first I'd like to. Other questions? All right. Okay. So what happens though what happens when we can't get past the 0th step? So what happens when we have a graph, we look at the theorem, and the theorem says, no, there are no Euler circuits. There are no Euler paths. Such things don't exist for this particular graph. Well, then we have to do something. We have to admit to ourselves that we can't get the optimal path that we may want, like let's say we're the security guard or something. We have to say, okay, well, we're going to have to retrace some of these blocks. And you want to minimize, right, the number that you retrace. You don't just want to walk back and forth 100 times, right? So then to accomplish that, we have this procedure, this Eulerizing graphs. And this is, okay, so this is a fancy way of just saying that we're going to what does this mean? It means we're going to add some edges to graph force Euler's theorem. Or the Euler's theorems for validity, let's say. So let me give you a really simple example of a very simple mail carrier problem. So let me draw a couple of lines here. We'll go to a less interesting neighborhood. Okay, so this is my neighborhood. Square city blocks. And let's do the security guard problem for this. Okay, so now the first question is, I've got a security guard. We know the problem. The guy wants to, let's say the security guard also lives in the neighborhood and wants to end up right back where he starts. He starts on that intersection there. He wants to end back in that intersection. He wants to traverse each block exactly once. That's his goal. Can you do it? That's the first one. So we want Fleury's algorithm. We want to apply it. We have to look at the 0th step. We look at the 0th step. Is Euler's theorem satisfied? See, one not. How many people say yes? How many people say no? Very good. I know why voter turnout is so low. For the worst. Younger generation. Come on. Assert yourselves. Okay, good. The 3 people that said no were correct. Good job. Way to go. Right. So why? Yeah.
Like on the outer edges.
Yeah.
It's connected.
Right. If we look at these guys, these vertices, these guys are no good. They have degree 3. Try to use that language if you can remember. Right. They have degree 3, each of these vertices. These guys, these corners have degree 2, they're okay. But the other ones, they're degree 3. So I'll put a blue dot there at all of the problem vertices. So even if we were looking for an Euler path, we'd be out of luck. We've got way too many odd vertices. All the other vertices are degree 2. That's great. So what we need to do is we want to force this graph to be an Euler graph, which means it satisfies the conditions for Euler's theorem. do that, we just add some edges. We look at, and we only add them to the problem vertices, okay? The blue ones in this case. You may not just be able to accomplish this with adding edges between two blue vertices. You may actually have to take paths between two blue vertices as well. So let's see what I mean here. So I'll put things in green that I'm going to add. I'm going to add an edge here. Say add an edge here. Now all of a sudden, if I look at these two vertices that I added the edge to, they're both degree 4. Is that clear? We're degree 3, now they're degree 4. I can do that up here too. Over here. So I've taken care of 8 of the edges, 8 of the problem vertices. Now they were odd, now they're even. However, I still have 4 left. And there are no edges. I'm not a security guard that goes through people's backyards, right? What I'm saying? I don't do this. That's bad security guarding. They taught me that. So what I'm going to do is I'm going to take a path. I'm going to add an edge here and an edge here. And when I do that, I have to be a little worried at first, because yes, I'm fixing this problem vertex and this problem vertex, but I'm also adding some edges to this vertex, but I added 2. So it was even before and it's still even. Now it has degree 4. Is it clear? So I do that there, and I do that here. And something's amiss. Oh no, I don't do that. I already did that. Okay, so now I need to do that here. I'm sorry, I shouldn't have done it over here. I wanted a minimal one, so let me do that and add this. I could have taken a longer path there, but I'd rather have. Okay. So now what I've done is I've added a bunch of edges to my graph. I didn't add new edges where there weren't ones before, so I just made certain edges multiple edges. But now, if I look at this graph, does it satisfy the condition in Euler's theorem? In other words, is every vertex even? Now, yeah, I've taken care of all of the problem ones, and anywhere place where I might have created a problem, I didn't. I just added an even number of path edges. So this does satisfy Euler, which means there's an Euler circuit. Which means there's an Euler circuit. So this is satisfies. But now let me ask you guys, some brave student, to explain to me what this does then, as far as answering the original problem, which is I want to be able to walk these streets only once. If I can't do that, what's the most efficient path? In other words, how can I make it so that I walk the minimal number of extra times for the blocks that I'm walking? Does this help me in any way? What does this Eulerizing of this graph do that kind of help me understand the answer to that question? No?
All I was gonna say is like the way it satisfies Euler's theorem is just making it a Euler circuit, like the graph.
So in this new graph, right, we have an Euler circuit, right? So now let's say we walked along that Euler circuit. Okay, what is that? What is, if so I use Fleury's algorithm with this new graph, right? I start at this red vertex. I find an Euler circuit. What is that telling me about my security guard? What is that saying to the security guard?
Ends where it begins.
It ends where it begins. So I did indeed, and I've covered each of the blocks, right? But have I covered each of the blocks exactly once? All right. So here's the thing. We got to separate our mathematical abstraction from the reality of what's happening, right? So what we did just a second ago when we Eulerized is we took a picture of our block and we just drew extra edges. That's our mathematical fun that we're having. What we did not do is we did not call up a construction company and say, hey, build a new road right along each of these edges, right? Build a road right here, knock down that house and build a road here, right? We didn't do that. We just did some silly math drawing. But now we have a new route. And so we take a route, right? Let's say this is the beginning of our Euler graph, our Euler path, or Euler circuit, sorry. Let's say that's the beginning. What happened here with our security guard, right around here? He walks up, he walks over, he walks up this block. He walks back, right? He's retracing that same block again. So these extra edges that we put in, they're telling us that he's going to walk that block twice, those blocks twice, right? So when we Eulerize, we're doing something abstract mathematically, but it's actually giving us concrete, I'm sorry, the pun. It's giving us extra information right, about where the security guard is doubling his path. All the other ones, he walks exactly once. And maybe when you're Eulerizing, there may be some blocks you want to walk twice. And you can kind of say, okay, well, let's Eulerize over there. Let's make that the extra. All right, cool. So this helps answer that problem. And there are a lot of different ways, as I sort of alluded to a second ago, of Eulerizing a given graph. I'm not going to go into all those details, but certainly the different ways of doing it can often be interesting as problems in and of themselves. So we also have this problem, this Bridges of Madison County problem. For that, we need the semi-Eulerizing solution. So there's Eulerizing and semi-Eulerizing. This mathematicians love semi and quasi and pseudo and all that. So semi-Eulerizing is the same thing as Eulerizing, except here we want to add edges. So Euler's theorem for paths is satisfied. Eulerizing is really for circuits. This is semi-Eulerizing is for paths. So here we have this problem with Bridges of Madison. Now, I didn't actually give the full details of this. Let me explain what the details were. So the actual details are, you're in this county. There's some land here, there's some land here. There are 4 islands. And you're a photographer and you want to take a picture of every bridge, but it costs $25 to cross a bridge. And you don't want to spend any more money than you have to. And the only extra rule is that you want to start on one side of the river and end on the other. So you want to start, over here and end here, or vice versa. So that's the basic setup for this problem. And what we need to do is first, we're going to make this problem to a graph problem, the graph theory problem. And the way we do that is we take each landmass and we make it a vertex, and take each bridge and make it an edge. So let's draw that. So I'll draw the 4 islands are going to be vertices. I'll label them A, B, C, and D. Then we have these two land masses on either side. Now I need to draw the bridges. So there's a bridge here from the northern landmass to A. It's C. C has a bridge to D. 2 bridges to the southern landmass, and 1 bridge. That's it. Sorry. D has a bridge to the southern landmass, and 1 to B. B has a bridge to the northern one. And then finally, there's this bridge here. And that bridge goes from the northern landmass to southern. Okay. So the first thing to do when we're looking at this problem is, let's say we were trying to find an Euler circuit, Euler path, and we knew that we wanted to start and end at the northern and southern landmasses. So we have these 2 vertices are going to be our starting and ending points. So what do you guys say about that? Any thoughts? If we were to apply Fleury's algorithm here, and we look at the 0th step, checking Euler's theorem, are we going to get through that step or get past that step? One had no, shaking no. See, yes, no. That's yes, no. How many people say yes? Will zero Euler's theorem is satisfied? Okay. How many people say no? It's not. 1.5. So I would like to hear from the yes, because that's why do you say it is that?
Okay, now I'm looking at it, and I saw, I was counting that everyone I thought was in agreement, but now I just found it's
Okay, so you did a good thing, and you were right, except you're not. It's like you get a lot of partial credit. You saw, I think, that this is not vertex. This is not vertex. The other vertices are all even. There are 2 odd vertices, and therefore there is an Euler path. However, there was one part of this problem that we wanted to keep in mind, which was that our photographer doesn't want to get stuck on island B, or is not starting on island B. Our photographer wants to start on one landmass and end on the other. And the part of Euler's theorem is that the 2 odd vertices are the beginning and the end of that Euler path. So while Euler's theorem is satisfied, in other words, there does exist an Euler path for this graph, it does not start and end at these 2 vertices that we're requiring. We would like to start and end at those 2 vertices. So we will semi-Eulerize this graph so that we can do that. And what do we do when we semi-Eulerize? We add edges so that we can do it. So does anyone have any suggestions of an edge we might add? D to what?
the bottom.
The bottom, yeah. Very good. Yes, I like it. E to S. That's very good, very clever. We just took D, which had degree 3, and made it have degree 4. Now it's E. And we took this vertex at the bottom, which had degree 4, made it degree 5, which now is an odd vertex. So now it does satisfy this, and we do get a path from the northern and southern land masses, either way, with a path. Now, what does that tell us? What can we tell the photographer? So that's a good math problem and math solution. What does that inform the photographer?
Like the southern landmass.
Right, that if you're going to do this, take pictures of every bridge, then to minimize your cost, you're gonna have to pay $25 extra because you're gonna have to travel one of these bridges twice. And the one bridge you'll have to travel twice, if you want to minimize the amount you're spending, is this bridge from the southern landmass to D. That's a good answer. And then we can say, we can apply Fleury's algorithm if we want and say, okay, well, okay, so let's say we did this, you go here, 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 here. There's an Euler path. It's not hard to apply the algorithm once you get a little, but you could make mistakes. Just make sure you're never crossing those extra bridges. Mathematics. Questions? Okay. Sure. Everyone's happy? At least questions? I did see that I had a couple of emails concerning questions about the homework. I will answer those. I had family in town over the weekend, so I was not able to get a lot of emails this weekend. But I'll try to answer, questions on homework. If you ask, you can always bring a homework question. I think Monday is a good time, actually. If you've looked over the homework, you have a question about it, you can bring it in on Monday. We could spend a little time talking about it. I'm not opposed to that. So feel free to do that or email me, and I'll try to be responsive at least before the deadline. Okay. So this is about it for chapter 5. And now we're going to move on to the next chapter, which has another flavor of questions, another set of types of questions, which seem very similar at first, but actually the answers are much more subtle here. Euler's theorem is a really nice theorem in that it's easy to apply. As we'll see, the next set of problems can be a little more tricky. There's more subtleties. But maybe these seem more I think this type of problem seems a little more natural. The type of problem has a general name. It's called the traveling salesman problem or salesperson problem. And it says abbreviated in the book TSPs. What are these about? So they're just about, okay, what do you need for one of these types of problems? So what do you need? The book kind of lists them out. You need a traveler, something that's traveling. It could be a package, it could be an electron in a circuit board, it could be all kinds of stuff, depending on the problem. A set of sites the traveler wants to visit. And you need a set of costs To get from one section to another. Very practical kind of problem. And the point of the problem is what you want to do in this problem is if you're the traveler is you want to visit each site once. And you want to do it for the lowest cost. That's the goal. So you probably have all had to solve this problem several times in your life, and you'll have to solve it, for the rest of your life. Like if you go grocery, if you have a shopping list and you have to visit multiple stores, for example, you have to choose the order in which stores you're going to, at which you don't want to go like one store, then go across town and then go back across town, right? So these types of problems are very practical problems that you solve all the time. But when you have a lot of different sites, they can become trickier. All right, so the book talks about several examples of these types of problems in the first section. And so one example is sort of what I just mentioned. You'll have you'll have several cities. So I did I just drew a silly graph, which makes no sense. Sorry, I'll draw it for you guys though. So we have Manhattan, then we have Topeka. I don't really know anything about Kansas. I'm not from here, but I went to Ann Arbor when I was for Michigan for undergrad, and then we had this rivalry with Ohio State, but we wouldn't even say Ohio State. We don't use their name. So I don't know if you guys use Lawrence, but I'm kind of trying to keep that up. But yeah, I don't really care. But I'm just yeah, Ohio State's the worst. I'll never go there. Roots. All right, anyway. Draw a graph. So this is not a complete graph, meaning there are some vertices that may not be connected, like Kansas City to Manhattan. Maybe I don't connect that because I have to go through Topeka, say. You don't have to, I guess you could do a plane route or something like that. So I draw a graph between all the cities. And then I'm going to, and this graph doesn't necessarily indicate a road, right? It could be I'm flying, whatever. But then I'm going to put a cost on every edge. And that cost could be, it depends on what I'm looking at. I just chose some sort of random thing of maybe how much it would cost, how many dollars it would cost gas, or if I stop for food or whatever, to get from one to another. So, I mean, this is not to scale, but I'm just trying to put it in there. It's not realistic. And then the idea is, okay, if you're starting at one, I mean, there's a lot of different problems you can ask. There's sort of a path problem, and then there's a circuit problem, right? So you can ask, if you want to get back to where you started, you can ask that question. And if you want to, or if maybe you don't care, you want to start somewhere and you want to end somewhere, but you want to visit each of these cities once, you want to do it for the lowest price. So now, let me ask you guys this. How is this different than the sort of street routing problems? How is this kind of a problem different than street routing? There's a couple of different answers here.
Because when you use on the street, street as long as we just didn't go down that street.
Okay.
And once we hit the vertex of like. width,
Okay, so, right, okay, I like what, the last thing you said. Hitting the vertex of Topeka. I like, I'm gonna grab onto that in particular. If we think about the street routing problem. We go up here. What is the goal of our security guard? The goal is to walk each of the blocks once, right? Each of the blocks. When we translate that into mathematical speak, we're looking for circuits or paths that hit each of the edges once in that graph. The traveling salesman problem, we don't care, we don't want, we actually really don't want to take each of the paths. I don't want to go here, here, and then here. I don't want to do that. That's a lot of money. What I want is I want to visit each of the vertices once. I want to hit each vertex once. I can hit edges where I don't have to hit each edge is what I want to say. And in fact, I probably won't hit each edge. So let's say I wanted a path here. I can give you a path that hits each one once pretty easily. Like that. And if I wanted to make it a circuit, I can go here. So that would be a solution to this problem, although I don't know if I've minimized costs. I have to look at that. There are other paths that go over there. So this type of a problem is, from a graph perspective, really different than the ones we've just addressed. And the types of, and so in particular, that means that Euler's theorem does not apply here if you're looking for the existence of a solution. It's a different kind of a problem that we have. But visiting vertices seems almost more natural, I think, than visiting every edge. So it's kind of, I think it's kind of a natural. So one thing that they'll do in this book, which I wanted to mention, is they might take a picture like this and they might turn this into a table. Okay, and how would they do that? So what they may do, let's draw this just so you know what they're doing. It looks a little funky. So let's say, how many cities do I have? 1, 2, 5, 6. Okay. So what they may do here is they might take each of these cities and write them this way. I probably won't do the whole thing here. Plain. And then they'll just fill in. They're basically looking and seeing what the cost is. Now, to go from a city to itself, there's no cost. So you're just gonna kind of put little asterisks on the diagonal here. But then Manhattan to Lincoln, we see a 60, and so we'll put 60 here. And let's say it costs the same to go one way as it does the other. And so on. So you can fill out the table. You know, I don't know, maybe I'll fill out the first row. And now here I don't have an edge from Manhattan to Kansas City, so I'll just put a little star there. So if you see tables like this, there's a way of taking a table like this and making, you know, a graph, and vice versa. A graph. So this is what they're doing. All right, so let me just say one thing, and then we'll pick up tomorrow, Wednesday, pardon me, from there, which is that these paths that visit every vertex exactly once, regardless of cost, are called something. So paths, I'm just going to make that definition now, which visit each vertex exactly once. These are called Hamilton paths. Have the great mathematician here and the drunkard. Okay. So we'll pick up Wednesday and tonight, yeah, it's just on chapter 5. If you struggle with it and you need a little extra time, I'm not going to be super picky about getting it in. Just don't let it go too long.
Write it on paper, like, make sure that
Sounds good. Hey, when you upload it, if you could do me a favor and try to have it so that it appears vertically. For some reason, Canvas, I have a real hard time actually rotating the uploaded homework. So try to get it so that I can read it.
Thank you.
You too.